At first glance, it seems like gravity should be unstoppable. If a cloud of gas is large enough, why couldn't it simply keep collapsing, gathering more and more mass until it becomes arbitrarily huge? After all, gravity scales with mass. The more material you collect, the stronger your pull becomes. In a purely gravitational universe, the biggest object would always win. But stars do not live in a purely gravitational universe. A star is not just a ball of matter. It is a nuclear reactor. The moment a collapsing cloud becomes hot enough to ignite hydrogen fusion, the rules change. Fusion is not passive. It releases energy on a scale that completely transforms the internal dynamics of the object. That energy does not stay locked inside. It radiates outward as photons, and photons carry momentum. Momentum is the key. Every photon leaving the core of a star pushes outward. One photon is insignificant. Trillions upon trillions per second are not. The more massive the star becomes, the hotter its core. The hotter the core, the faster nuclear fusion proceeds. And fusion increases luminosity dramatically. Not slightly, not proportionally, dramatically. There is a brutal non-linearity here. If you double the mass of a massive star, you do not simply double its brightness. Luminosity increases much faster than mass. That means radiation pressure grows disproportionately compared to gravity. Gravity strengthens linearly with mass. Luminosity, and therefore outward photon pressure, increases far more steeply. Eventually, radiation becomes strong enough to push back against infalling gas. This is why stars cannot grow forever. During formation, a protostar gathers material from a surrounding cloud. Gas spirals inward, feeding the growing core. But as the protostar gains mass and its temperature rises, it becomes brighter. Its radiation heats and ionizes nearby gas. Heated gas expands. Ionized gas interacts more strongly with light. The infalling material begins to experience resistance. At extreme luminosities, the outward pressure from radiation can halt accretion entirely. This creates a self-limiting system. The more mass a protostar gains, the more effectively it prevents further growth. It turns its own energy into a barrier, but that is only the first layer of limitation. There is also structural instability. Extremely massive stars are precariously balanced. Their internal fusion rates are so high that small changes in temperature can produce large changes in energy output. A slight compression of the core increases fusion. Increased fusion increases pressure. Increased pressure drives expansion. Expansion cools the core, reducing fusion again. The star lives in a constant state of near instability. Beyond a certain mass, that instability becomes violent. Radiation does not just push outward gently, it drives stellar winds, continuous outflows of gas from the surface. In the most massive stars, these winds can remove enormous amounts of material over relatively short timescales. Instead of growing, the star begins eroding itself. The more massive it becomes, the more aggressively it sheds matter. So we have two independent limits forming. First, formation feedback. Radiation prevents further accretion. Second, evolutionary feedback. Radiation strips away existing mass. Gravity builds the star. Light limits it. And this balance is not philosophical. It is measurable. It is embedded in equations that describe hydrostatic equilibrium, opacity, and momentum transfer. It appears in simulations of star formation. It appears in observations of massive stellar clusters. The universe does not allow stars to grow indefinitely because stars are powered by fusion, and fusion produces radiation, and radiation fights gravity. There is a deeper symmetry here. If gravity were the only force, matter would collapse into singularities everywhere. If radiation were dominant everywhere, structure would never form. Stars exist precisely because those forces balance, but that balance becomes harder to maintain as mass increases. Every additional solar mass makes the internal furnace hotter. Every increase in temperature strengthens the outward flow of photons. The star begins to approach a threshold where light becomes as powerful as gravity. That threshold is not a suggestion. It is a wall, or at least it was believed to be. And for decades, everything we observed seemed to confirm that no star could push past that wall for long. The ceiling was not arbitrary. It emerged from the basic fact that light carries force, and that force grows disproportionately fast in massive stars. So the idea that a star could grow to hundreds of solar masses sounded less like a curiosity and more like a violation of the rules. Before R136A1, the assumption was simple. Stars cannot grow forever. Not because gravity is weak, but because light is stronger than we intuitively imagine. And once light begins to win, growth stops. A star is a battlefield, not metaphorically, physically. On one side, gravity pulls inward. Every particle inside a star is attracted toward every other particle. The larger the mass, the stronger that pull. Gravity does not care about temperature or brightness. It simply compresses. It tries to collapse the star into a denser state. On the other side, radiation pushes outward. This outward push is not wind in the traditional sense. It is light itself. Photons generated in the core carry energy and momentum. When they scatter off electrons or are absorbed and re-emitted by atoms, they transfer momentum. That transfer creates pressure, and pressure is force per unit area. Inside a star, this force is enormous. The core of a massive star reaches tens of millions of degrees. At those temperatures, fusion reactions occur at astonishing rates. Energy generation becomes explosive compared to stars like the Sun. That energy must escape, and as it does, it exerts pressure on the surrounding layers. This balance between inward gravity and outward pressure is called hydrostatic equilibrium. Without it, stars would either collapse instantly or explode outward. In small stars, gravity is strong relative to radiation pressure. The outward push is significant, but it does not threaten the star's structural integrity. In very massive stars, however, radiation pressure becomes a dominant contributor to the internal pressure budget. And here's where intuition fails. Gravity increases proportionally with mass. Double the mass, double the gravitational pull at a given radius, but radiation pressure does not scale linearly. Luminosity increases far more steeply than mass. In high-mass stars, luminosity roughly scales as mass to the third or even fourth power, depending on the regime. That means if you double the mass, you might increase luminosity by 8 times or more. So gravity doubles. Radiation pressure increases 8-fold. This imbalance is the key to the upper mass limit. As a star grows more massive, it becomes disproportionately brighter. That brightness increases the outward push of photons far faster than gravity strengthens. At some point, the outward momentum transfer becomes comparable to the inward pull of gravity in the star's outer layers. When that happens, stability weakens. Radiation pressure can lift material from the surface. It can drive stellar winds that eject mass into space. These winds are not rare events. They are continuous flows. In the most massive stars, mass loss rates can reach 10 to the power of -5 to 10 to the power of -4 solar masses per year. That may sound small, but over a few million years, it becomes enormous. The star begins to erode itself. Now imagine this happening during formation. A protostar is trying to gather material from a surrounding accretion disk. Gravity pulls gas inward, but as the star's luminosity rises, radiation pushes back. Gas heated by radiation becomes ionized. Ionized gas couples more strongly to photons. The inflow slows. Eventually, radiation pressure can halt accretion entirely. This is not a catastrophic explosion. It is a steady resistance. The protostar shines so brightly that it sterilizes its own fuel supply. The Eddington limit formalizes the point where radiation pressure equals gravitational attraction for ionized hydrogen. If luminosity exceeds this critical value, outward force wins locally. Matter can no longer remain bound in the outer layers. For massive stars, approaching this limit is not optional, it is inevitable. Their fusion rates push them toward it, but radiation pressure is not uniform throughout the star. It depends on opacity, how easily photons interact with matter. In regions of high opacity, photons are trapped longer, increasing pressure. In regions of lower opacity, radiation escapes more freely. This creates a complex internal structure where gravity and radiation are locked in dynamic competition. The star is not a static sphere. It is a self-regulating engine constantly adjusting to maintain balance. Push the mass too high, and regulation becomes impossible. There is another layer to this fight: geometry. Radiation tends to escape along the path of least resistance. If a star forms with an accretion disk, radiation can preferentially escape along the poles, while material continues falling in along the disk plane. This can allow a protostar to grow slightly larger than a simple spherical model would predict. But even with geometric loopholes, the imbalance between gravity and radiation pressure becomes extreme at very high masses. At around 100 solar masses, radiation pressure is already a significant fraction of the total internal pressure. At 150 solar masses, it becomes dominant in the outer layers. The star is living on the edge of the Eddington limit. Any further increase in luminosity amplifies mass loss dramatically. The physics becomes unforgiving. Gravity wants more mass, radiation wants to shed it, and the more massive the star becomes, the more violently this tug-of-war intensifies. This is why the upper mass limit was not arbitrary. It emerged from the scaling laws themselves. As mass increases, the internal furnace becomes too powerful. Light becomes too strong. Eventually, gravity is no longer the only master. And for decades, every model said the same thing. There is a point where radiation wins often enough to prevent indefinite growth. The question was not whether gravity and radiation fight. The question was whether gravity could ever temporarily overpower light long enough to build something truly extreme. Before R136A1, the safe answer was no. Luminosity is the hidden amplifier in stellar physics. It is not simply how bright a star appears. It is a measure of how much energy it releases every second. And in massive stars, luminosity does not grow gently as mass increases. It explodes upward. In lower mass stars like the Sun, there is a relatively stable relationship between mass and brightness. But once you enter the regime of massive stars, that relationship becomes brutally nonlinear. A star 10 times more massive than the Sun can be tens of thousands of times more luminous. A star 100 times more massive can outshine the Sun by millions of times. This steep scaling is known as the mass-luminosity relationship. In massive stars, luminosity can scale roughly with the cube of the mass, sometimes even steeper depending on internal structure. That means small increases in mass create enormous increases in energy output. And energy output is not passive. It directly influences how much radiation pressure builds up inside the star. The core of a massive star reaches temperatures exceeding 30 or 40 million Kelvin. At these temperatures, hydrogen fusion proceeds primarily through the CNO cycle, unlike the proton-proton chain dominant in smaller stars. The CNO cycle is extremely temperature sensitive. A slight rise in core temperature dramatically increases fusion rates. Fusion rates determine luminosity. Luminosity determines radiation pressure. This creates a feedback system. If the core contracts slightly, temperature rises. Rising temperature accelerates fusion. Accelerated fusion increases energy output. Increased energy output raises radiation pressure. Radiation pressure pushes outward, expanding the core and lowering temperature again. The star oscillates around equilibrium, but at high masses, this oscillation becomes increasingly unstable. Because luminosity grows so quickly with mass, radiation pressure grows faster than gravity can compensate. Gravity increases in proportion to mass, but luminosity increases disproportionately. This is the core reason stars cannot simply keep growing. The physics punishes excess mass with excessive brightness. Brightness also drives mass loss in a very direct way. High luminosity increases the number of high-energy photons in the stellar atmosphere. These photons interact with atomic transitions in the outer layers, transferring momentum to gas. The result is a radiation-driven wind that carries matter away from the star at high velocity. In the most luminous stars, these winds can reach thousands of kilometers per second. Over a few million years, such winds remove a significant fraction of the star's total mass. This is not a marginal effect. It fundamentally shapes stellar evolution. Massive stars do not quietly burn until they collapse. They peel themselves apart over time. The mass-luminosity relationship also implies something even more dramatic. The lifetime of a star decreases sharply as mass increases. While the Sun will live for roughly 10 billion years, a star 100 times more massive may live only a few million. The star is brighter because it burns fuel at a far faster rate. It is more massive, but it consumes its hydrogen disproportionately quickly. So increased mass does not simply mean more star. It means exponentially more energy output, exponentially more radiation pressure, and exponentially greater instability. This steep scaling explains why the theoretical upper mass limit felt so convincing. Once stars approach extreme masses, luminosity becomes almost self-destructive. The star shines so fiercely that it undermines its own structural integrity. There is no gentle path beyond this regime. To move from 150 solar masses to 200 would not be a modest extension. It would require surviving a dramatic increase in luminosity and radiation pressure. The star would need to maintain hydrostatic equilibrium under conditions where photons are exerting extraordinary outward force. The mass-luminosity relationship is therefore not just a correlation, it is a constraint. It links mass to instability. It ensures that extreme mass carries extreme consequences. For decades, this relationship reinforced the idea that stars above a certain threshold should be nearly impossible to sustain. The mathematics did not leave much room for optimism. Each additional solar mass came with a disproportionate increase in internal violence. This is what made the existence of any star significantly beyond the classical boundary so unsettling. To exceed the expected ceiling would mean that the mass-luminosity scaling, while still true, was being navigated in ways that allowed temporary survival at intensities once thought unsustainable. The universe had drawn its curve steeply upward. The question was whether something could ride that curve further than we believed possible. The Eddington limit is not a suggestion. It is a balance point written directly into the physics of light and gravity. At its core, the idea is simple. Gravity pulls matter inward. Radiation pushes matter outward. When these two forces become equal in magnitude for ionized gas, a threshold is reached. If luminosity rises beyond that threshold, radiation pressure overwhelms gravity in the outer layers, and matter can no longer remain bound. The limit depends on mass. A more massive star can tolerate higher luminosity because gravity is stronger. But luminosity increases steeply with mass, and at extreme values, the outward push of photons catches up. Mathematically, the Eddington luminosity is derived by equating gravitational force and radiation force acting on a particle of ionized hydrogen. Gravity pulls it inward with a force proportional to the mass of the star. Radiation exerts an outward force proportional to luminosity and opacity. When the two match, the star reaches the Eddington limit. For hydrogen-dominated plasma, this produces a critical luminosity that scales directly with mass. If a star radiates above this value, the surface layers become unstable. Gas begins to flow outward, accretion halts, mass loss accelerates. This does not mean the entire star explodes instantly. Instead, the outer envelope becomes difficult to confine. Regions near the surface may locally exceed the limit even if the total luminosity is slightly below it. In such cases, radiation-driven winds intensify. Massive stars live close to this threshold. In fact, some of them hover near it throughout their lives. They are not comfortably below it. They operate near the edge. As mass increases, the ratio between actual luminosity and Eddington luminosity approaches unity. The star becomes Eddington limited. Its growth is no longer governed only by gravity and fuel supply, but by how much radiation it can tolerate before shedding material. This has enormous implications during formation. A protostar that approaches the Eddington limit cannot easily continue accreting matter in a simple spherical geometry. Radiation heats the surrounding gas, increases pressure, and pushes back. The protostar effectively turns on a light-based shield that resists further growth. But the limit is not perfectly rigid. It depends on opacity, and opacity depends on composition. If the surrounding gas has lower metallicity, opacity decreases. Radiation escapes more easily. In that scenario, the effective Eddington limit shifts slightly. The star might temporarily exceed the classical value before feedback catches up. There is also the role of anisotropy. If accretion happens through a disk, radiation may escape preferentially along the poles. This can allow material to continue flowing inward along the equatorial plane, partially bypassing the spherical Eddington constraint. However, even this geometry cannot remove the fundamental scaling between luminosity and mass. The deeper truth is that the Eddington limit does not prevent stars from existing above a specific number in an absolute sense. It prevents them from being stable and growing indefinitely. If a star exceeds the limit, it reacts by shedding mass until equilibrium is restored. That is why the classical ceiling around 150 solar masses felt so natural. Above that mass, stars would be so luminous that they would constantly hover near or above the Eddington limit. Sustained growth beyond it seemed improbable. Any excess mass would simply be blown away. The limit, therefore, acts as a thermostat for stellar mass. Too much brightness, and the star cools itself by losing material. Too little brightness, and gravity compresses the star until fusion accelerates again. In this way, the Eddington limit reinforces the idea that nature regulates extremes. Massive stars can form. They can become enormous. But there exists a feedback mechanism rooted in the physics of light itself that resists runaway growth. For decades, this reasoning shaped expectations. Stars could approach the limit. They could flirt with it. But crossing it significantly and surviving appeared unlikely. The concept was elegant. Light, the very thing that allows us to see stars, was also the thing that capped their size. And if that cap could be exceeded, even temporarily, it would mean that our understanding of how radiation and gravity negotiate with one another was incomplete. For a long time, the number did not look arbitrary. Around 150 times the mass of the Sun became the accepted ceiling, not because someone declared it, but because independent lines of reasoning kept converging there. Theoretical models of stellar structure showed that once a star approached that scale, radiation pressure began to dominate the outer layers. Luminosity climbed so steeply that the ratio between the star's actual brightness and its Eddington luminosity approached unity. In practical terms, this meant the star was constantly on the edge of blowing material away. But theory alone would not have been enough. The limit gained credibility because observations seemed to agree. Astronomers surveyed young, massive clusters in the Milky Way and nearby galaxies. They measured luminosities, temperatures, and spectral signatures. They estimated masses using stellar evolution tracks and atmosphere models. Again and again, the most extreme stars appeared to cluster near the same upper boundary. Some objects were close to 100 solar masses. A few pushed toward 120 or 140. But clear, repeatable detections well above 150 solar masses were absent. It began to look like nature had drawn a soft but reliable line. There were also statistical arguments. The initial mass function, the distribution describing how many stars form at each mass, falls off steeply at high masses. Extremely massive stars are rare by construction. Even if the physics allowed slightly larger objects, the probability of forming them would be small. That statistical scarcity reinforced the perception of a practical ceiling. Another reinforcing factor came from stellar winds. Observations of luminous blue variables and Wolf-Rayet stars revealed violent mass loss episodes. Some massive stars were seen ejecting enormous shells of gas. Eta Carinae, for example, underwent a dramatic eruption in the 19th century, briefly becoming one of the brightest stars in the sky. These events demonstrated that once stars reached extreme luminosities, they shed mass aggressively. If stars near 100 solar masses were already unstable, then stars significantly beyond that should have been even more so. Computer simulations of star formation also supported the ceiling. When gas clouds were allowed to collapse under realistic conditions, including radiation feedback, turbulence, and magnetic fields, the resulting stars rarely exceeded the predicted limit. Radiation from the forming protostar disrupted accretion flows, heated surrounding gas, and carved cavities in the cloud. The more massive the protostar became, the more effective this feedback appeared. So the 150 solar mass boundary became embedded in the discipline. It was not framed as an unbreakable law, but as a physically motivated expectation backed by data. Textbooks described it, papers referenced it. When new massive stars were discovered, their estimated masses were often compared against this threshold as a sanity check. There was also a conceptual elegance to the number. It suggested that even in the most extreme cases, stars were bound by self-regulation. Gravity built them up. Radiation prevented excess. The interplay between these forces produced a natural maximum. Importantly, the ceiling did not need to be perfectly sharp. It could fluctuate slightly depending on metallicity or environmental conditions. But the overall idea remained. Sustained stellar masses far above 150 solar masses should be extremely difficult to achieve and even harder to maintain. That confidence shaped interpretation. If a measurement suggested a star far beyond the limit, the first instinct was caution. Perhaps the object was unresolved and actually multiple stars blended together. Perhaps the distance estimate was off. Perhaps the stellar atmosphere model overestimated luminosity. Extraordinary masses demanded extraordinary scrutiny. This mindset was not resistance to discovery. It was discipline. When theory and observation agree for decades, skepticism toward outliers is healthy. It protects the field from premature conclusions. By the early 21st century, the upper mass limit had become one of those quiet assumptions underlying many branches of astrophysics. It influenced predictions about supernova energetics, black hole formation, and the chemical enrichment of galaxies. If stars could not exceed a certain mass, then there were limits on how massive stellar remnants could be as well. The ceiling around 150 solar masses therefore functioned as more than a number. It was a structural element in our broader understanding of how galaxies evolve. And yet, as observational technology improved, astronomers began probing regions of star formation beyond the Milky Way, where conditions were more extreme. Dense clusters, intense radiation fields, slightly different chemical compositions, environments where the standard assumptions might be tested. The limit still looked solid, but it had not yet faced its most violent laboratory. When stars approach the extreme upper end of the mass scale, they do not sit quietly. They lose mass constantly. Stellar winds become not a secondary feature, but a defining characteristic of their existence. In lower mass stars like the Sun, winds are relatively gentle. The Sun loses only a tiny fraction of its mass over billions of years. Its wind shapes the heliosphere but barely affects the star's long-term structure. In very massive stars, the situation is completely different. Their luminosity is so intense that radiation itself becomes an engine of mass removal. These winds are driven by photon momentum. High-energy photons streaming outward interact with ions in the stellar atmosphere. When photons are absorbed or scattered by atomic transitions, they transfer momentum to the gas. This repeated transfer accelerates material outward. The more luminous the star, the stronger this effect becomes. For extremely massive stars, the mass loss rates can reach astonishing values, on the order of 10 to the -5 or even 10 to the -4 solar masses per year. Over a few million years, that can amount to tens of solar masses lost to space. In some cases, episodic eruptions can remove even larger amounts in short bursts. This is not just erosion, it is structural transformation. As outer layers are stripped away, the chemical composition at the surface changes. Hydrogen-rich envelopes can be peeled off, exposing helium-burning cores beneath. The star evolves not only because it burns fuel internally, but because it is physically reshaped by the material it expels. There is a compounding effect here. As mass decreases, gravity weakens slightly, but luminosity may remain high relative to the star's mass. This can push the star even closer to the Eddington limit, intensifying winds further. The star enters a feedback loop in which brightness fuels mass loss, and mass loss alters structure. This is one reason the upper mass limit seemed so secure. Even if a star were somehow assembled at 200 solar masses, it would not remain there for long. Radiation-driven winds would strip it down rapidly. The star might briefly exceed the theoretical ceiling, but sustained existence at such mass appeared unlikely. Observational evidence reinforced this view. Luminous blue variables, for example, exhibit violent outbursts, during which they shed large amounts of material. Eta Carinae's 19th-century eruption expelled several solar masses in a relatively short time. Wolf-Rayet stars, often the evolved descendants of massive stars, show strong, high-velocity winds that continue removing mass at extraordinary rates. These phenomena demonstrated that the most luminous stars live in a state of near instability. Their surfaces are not calm. They are continuously pushed outward by radiation pressure that almost equals gravity. There is also the issue of clumping in stellar winds. Observations show that mass loss is not perfectly smooth. Gas can be ejected in dense clumps, making the process more chaotic and potentially more efficient at removing mass than earlier models predicted. This added complexity strengthened the argument that very massive stars would struggle to maintain extreme masses for long. The wind mechanism therefore served as both a formation barrier and an evolutionary regulator. During formation, radiation could halt accretion. During life, radiation could strip away accumulated mass. The star could not simply ignore the consequences of its own brightness. All of this made the classical ceiling feel almost inevitable. If radiation pressure limited growth and stellar winds limited survival, then the maximum stellar mass was constrained on two fronts. The universe appeared to regulate its own extremes. The implication was clear. Any star that significantly exceeded the expected boundary would either never form or would rapidly shed enough material to fall back within the safe range. That was the rule, and it seemed to hold. until observations began pointing toward an object whose estimated mass did not comfortably sit below that boundary. If such an object truly existed, then either mass loss rates had been overestimated, or formation mechanisms were more efficient than expected, or both. The winds that once appeared to enforce the limit would need to be reconsidered in a more nuanced framework. Before that reconsideration, however, the physics of stellar winds stood as one of the strongest arguments that stars could not grow or remain indefinitely massive. During the earliest phase of a star's life, long before it shines steadily on the main sequence, another barrier to extreme growth emerges: formation feedback. A star does not appear fully formed. It must gather mass from a surrounding cloud of gas. In the beginning, gravity dominates. A dense core forms inside a collapsing molecular cloud, and gas begins spiraling inward through an accretion disk. The protostar grows rapidly, but growth is not passive. As mass accumulates, the protostar heats up, and once nuclear fusion ignites, the situation changes dramatically. Fusion turns the protostar into a source of intense radiation. That radiation does not simply illuminate space, it heats and ionizes the surrounding gas. Ionized gas interacts more strongly with light. Heated gas expands. Pressure rises in the immediate environment of the protostar, and the inflow of material becomes increasingly unstable. This is the essence of radiative feedback. As the forming star becomes more luminous, it begins to disrupt the very cloud feeding it. Ultraviolet photons carve out ionized regions around the star, creating expanding bubbles of hot plasma. These regions, known as H2 regions, can grow and push against infalling gas. The stronger the radiation, the larger and more disruptive these bubbles become. In massive star formation, this effect is especially pronounced. A protostar that is already tens of times the mass of the Sun emits enormous amounts of ultraviolet radiation. The surrounding gas does not remain cool and cooperative. It becomes heated, pressurized, and dynamically altered. Accretion becomes a race against feedback. There is also mechanical feedback. Massive protostars drive bipolar outflows, powerful jets that eject material along the rotational axis. These jets punch through the surrounding cloud, removing angular momentum and mass. While jets help regulate disk accretion, they also expel material that might otherwise have contributed to further growth. The formation environment becomes chaotic. Cloud fragmentation further complicates the picture. Molecular clouds are turbulent. As they collapse, they often split into multiple dense cores rather than forming a single dominant object. Instead of one protostar consuming all available gas, many stars form in proximity, competing for material. In dense clusters, gravitational interactions between young stars can redirect gas flows or even eject protostars from the densest regions. This competition limits how much mass any one object can realistically accumulate. Even in the densest star-forming regions, feedback from nearby massive stars contributes to disruption. A single luminous star can heat and ionize large volumes of gas, suppressing additional accretion in its neighborhood. Star formation becomes self-limiting on cluster scales as well as individual scales. All of these processes point toward the same conclusion. Assembling extremely large stellar masses is not simply a matter of having enough gas. It requires overcoming radiation pressure, thermal expansion of surrounding material, mechanical outflows, and gravitational competition within clusters. For a long time, models suggested that once a protostar approached roughly 100 solar masses, radiative feedback became so strong that continued accretion would be severely restricted. The protostar would effectively shut off its own growth. There were proposed loopholes. Accretion through a disk could allow radiation to escape preferentially along the poles, reducing feedback along the plane where gas continued flowing inward. In very dense clusters, stellar mergers might combine already massive stars into a larger object. But these scenarios were considered special cases, not the default pathway for forming stable, extremely massive stars. The prevailing expectation was that formation feedback imposed a practical upper bound. Even if radiation pressure during the main sequence did not immediately destroy the star, the formation stage itself would likely prevent it from ever reaching such extreme mass. Thus, the classical upper mass limit was supported not only by stellar structure and winds, but by the physics of birth. A star had to pass through formation before it could challenge evolutionary constraints. If formation already capped mass, then extreme objects should be vanishingly rare or impossible. This reinforced the confidence in the ceiling. Gravity begins the process, but light quickly becomes an obstacle. The brighter the protostar, the more it sterilizes its own fuel supply. It heats the cloud, drives away material, and competes with itself. To build a star far beyond the accepted limit would require a formation environment capable of temporarily suppressing or bypassing these feedback mechanisms. It would require density high enough, accretion flows strong enough, or mergers frequent enough to overcome radiation's resistance. For decades, no clear observational evidence forced astronomers to believe such conditions routinely produce stars significantly above the expected boundary. Formation feedback, combined with radiation pressure and stellar winds, appeared to close the door. The rule was consistent across theory, simulation, and observation, until a region was examined where star formation was operating at a level far more violent than previously studied, a region where gravity might briefly outrun light. The Large Magellanic Cloud is not just another neighboring galaxy, it is a laboratory. Orbiting the Milky Way at a distance of roughly 160,000 light-years, the Large Magellanic Cloud is smaller, less massive, and chemically different from our own galaxy. That difference is critical. One of the most important distinctions is metallicity. In astronomy, metals mean everything heavier than hydrogen and helium. The Large Magellanic Cloud has lower metallicity than the Milky Way. That means its gas contains fewer heavy elements. Why does that matter? Because opacity depends on composition. Heavy elements provide many of the atomic transitions that absorb and scatter photons. Fewer metals mean lower opacity. Lower opacity means radiation can escape more easily. And if radiation escapes more easily, radiation pressure couples less efficiently to gas. That subtle shift changes the balance between gravity and light. In the Milky Way, massive stars are born in environments where radiation interacts strongly with surrounding material. Feedback kicks in aggressively. In the Large Magellanic Cloud, slightly lower metallicity weakens that feedback. It does not remove it, but it changes the efficiency. This alone makes the galaxy interesting for testing the upper mass limit. But metallicity is not the only factor. The Large Magellanic Cloud contains some of the most intense star-forming regions in the local universe. gas clouds there are dense, turbulent, and capable of producing extremely massive clusters. The dynamics inside these regions are violent. Stellar winds, radiation fields, and gravitational interactions all overlap in a crowded environment. In such conditions, rare events become more probable. High stellar density increases the likelihood of close encounters and even mergers between young, massive stars. If two already massive protostars collide or merge early in their lives, the resulting object can exceed the mass expected from simple accretion alone. This is one of the loopholes theorists had considered but rarely observed clearly. The Large Magellanic Cloud also offers observational advantages. Its relative proximity allows telescopes like Hubble Space Telescope to resolve dense star clusters with high precision. At 160,000 light-years, individual massive stars can be studied spectroscopically. Their temperatures, luminosities, and wind properties can be measured in detail. This combination, slightly different chemistry, extreme star-forming regions, and observational accessibility, makes the Large Magellanic Cloud uniquely valuable. It is not just a different galaxy, it is a stress test for stellar physics. If the upper mass limit were ever to bend, this is the kind of environment where it would happen. Lower metallicity reduces radiative coupling, extreme density increases accretion rates. High cluster mass increases the probability of mergers. Each factor alone might not shatter the ceiling. Together, they create conditions far more aggressive than those typically found in the Milky Way. For decades, the classical upper limit was built largely on observations within our own galaxy. That dataset was rich, but not universal. The Large Magellanic Cloud provided a new arena, and inside it lies one of the most violent star-forming regions known, a place where gravity briefly appears to outrun light. That place is the Tarantula Nebula. But before we reach it, one thing must be clear. The Large Magellanic Cloud is not an anomaly. It is a reminder that the universe is not chemically uniform. Stellar physics does not unfold under identical conditions everywhere. Small changes in composition and density can shift the balance between radiation and gravity in ways that only become visible at extreme scales. If a star were to exceed the traditional limit, it would likely be born in a galaxy like this, close enough to study, different enough to matter, and violent enough to challenge our assumptions. The Tarantula Nebula is not just a beautiful cloud of gas. It is the most violent stellar nursery in the local group. Formerly known as Tarantula Nebula or 30 Doradas, this region inside the Large Magellanic Cloud is the brightest and most active star-forming complex within several million light-years. If it were located at the distance of the Orion Nebula, it would cast visible shadows on Earth. Its scale is staggering. The Tarantula Nebula spans over 1,000 light-years. At its center lies an immense concentration of hot, young, massive stars blasting their surroundings with ultraviolet radiation. These stars are not quietly forming. They are detonating into existence in a dense, turbulent environment shaped by shock waves, winds, and previous generations of supernova explosions. This is not a calm molecular cloud. It is a battlefield. Gas densities in parts of the Tarantula Nebula are far higher than in typical Milky Way star-forming regions. Turbulence compresses gas into massive clumps capable of collapsing into extremely large stellar cores. Accretion rates in such regions can be significantly higher than average, meaning protostars can gather mass faster before feedback mechanisms fully disrupt inflow. Speed matters. If a protostar can accumulate mass rapidly enough, it may temporarily outrun radiation feedback. Gravity can win, not permanently, but long enough to build something exceptional. The environment is also chemically different. As mentioned earlier, the Large Magellanic Cloud has lower metallicity than the Milky Way. In the Tarantula Nebula, this reduced metal content decreases opacity. Photons escape more easily. Radiation pressure couples slightly less efficiently to the gas. That subtle shift can allow higher accretion rates before radiation becomes dominant. The nebula is also young and energetic. Many of the stars in its core are only a few million years old. They are massive, hot, and luminous. Their collective radiation sculpts the surrounding gas into intricate filaments and cavities. Stellar winds from these giants collide, creating shock fronts that compress other regions of gas, triggering new waves of star formation. It is a feedback cascade. Massive stars form, blast their environment, compress nearby gas, and potentially seed the next generation of even more massive stars. The Tarantula Nebula is not just forming stars, it is amplifying extremes. At its heart lies a dense cluster known as R136. This cluster is not casually dense. It is packed with some of the most massive stars ever observed. The stellar density in its core is so high that gravitational interactions between massive stars are far more frequent than in typical clusters. This density increases the probability of stellar mergers. In less crowded regions, two massive protostars are unlikely to collide. In the core of the Tarantula Nebula, the odds are not negligible. If mergers occur early in a star's life, they can assemble an object more massive than standard accretion models would allow. The Tarantula Nebula therefore represents a convergence of factors: high gas density, rapid accretion, lower metallicity, extreme stellar crowding, violent feedback cycles. Each factor alone challenges the classical ceiling. Together, they create the most favorable environment nearby for bending the upper mass limit. For decades, astronomers suspected that if an outlier existed, a star exceeding the accepted boundary, it would be born in a place like this. The Tarantula Nebula is not ordinary star formation scaled up slightly. It is star formation at maximum intensity. And inside this storm of gravity and light, one particular cluster would eventually reveal a star whose estimated mass forced astrophysics to pause. Not because the theory was wrong, but because the universe had found a corner where the rules were stretched to their limit. At the center of the Tarantula Nebula lies something even more extreme than the surrounding chaos: the R136 cluster. R136 is not a loose collection of stars scattered across a wide region. It is a compact, intensely crowded core packed with some of the most massive and luminous stars ever identified. Its central region spans only a few light years, yet it contains dozens of stars with masses tens of times greater than the Sun, and several far beyond that. The density is the first thing that matters. In most stellar clusters within the Milky Way, massive stars are separated by significant distances. Interactions are rare. In R136, massive stars are packed together in a volume so small that gravitational interactions become statistically important. Close encounters are more likely. Dynamical friction alters trajectories. In extreme cases, stellar mergers become possible. That density alone changes the formation story. If two very massive protostars collide early in their evolution, the resulting merged object can exceed the mass predicted by simple accretion limits. This provides a pathway to building an object larger than radiation feedback alone would typically allow. Instead of one star gathering all its mass directly from gas, it can inherit mass from another already massive star. The cluster is also extremely young. R136 is estimated to be only around 1 to 2 million years old. That youth is crucial. Massive stars live fast and die young. If the cluster were much older, its most extreme members would already have exploded as supernovae. The fact that R136 is so young means we are observing it near the beginning of its evolutionary timeline, when the most massive stars are still present and near their peak luminosity. Youth also means minimal time for long-term mass loss. Even though radiation-driven winds are intense, the cluster has not existed long enough for its most massive stars to shed enormous fractions of their mass. If a star formed at 200 or even 300 solar masses, it might still retain most of that mass at an age of 1 million years. This timing matters. The cluster's total mass is also enormous. R136 contains hundreds of thousands of solar masses worth of stars within a relatively small region. Such a large gravitational reservoir increases the probability that unusually massive cores could form in the first place. The deeper gravitational potential well of the cluster helps confine gas and may support higher accretion rates during formation. Another important factor is the cluster's dynamical state. R136 appears to be mass segregated, meaning the most massive stars are concentrated toward the center. Whether this segregation is primordial or the result of early dynamical evolution is still debated. If the classical upper limit were strictly enforced, this object should not exist, at least not in the way it appeared. R136 provided the conditions. The Tarantula Nebula provided the violence. The Large Magellanic Cloud provided the chemical differences. All the ingredients for bending the rule were present, and within that dense core, astronomers would identify a star whose estimated mass did not sit comfortably below 150 solar masses. It pushed beyond. And that is where the confidence in the ceiling began to crack. Before R136 was understood as a dense cluster of individual massive stars, it looked almost mythical. Early observations of the central region of the Tarantula Nebula showed an intensely bright core. The resolution of mid-20th century telescopes was not sufficient to separate the light into distinct stellar sources. What astronomers saw was a compact, brilliant object embedded in glowing gas. For a time, some even speculated that R136 might be a single superstar, a hypothetical object far more massive than anything known. That idea did not survive improved imaging, but it revealed something important. The central luminosity was extreme. As observational techniques improved, especially with high-resolution ground-based telescopes and later space-based instruments, the bright core was resolved into a cluster of individual stars. R136 was not one supermassive star. It was a dense concentration of many very massive stars packed into a small volume. Even so, the total luminosity of the core remained astonishing. astronomers began cataloging individual members of the cluster. Spectroscopy allowed them to measure surface temperatures and chemical signatures. These early measurements showed that several stars in R136 were extraordinarily hot. Surface temperatures exceeding 40,000 Kelvin, some approaching or surpassing 50,000 Kelvin. These were not ordinary O-type stars. They were among the most extreme examples of their class. Based on luminosity and temperature, rough mass estimates were calculated using stellar evolution models. Some of these estimates pushed into uncomfortable territory, above 100 solar masses and in a few cases possibly approaching 150. But caution dominated interpretation. Mass estimation for very massive stars is not simple. It depends on models of stellar atmospheres, assumptions about distance, extinction corrections for dust, and evolutionary tracks. Small changes in input parameters can significantly affect inferred mass. In the early years, uncertainties were large enough that most astronomers preferred conservative estimates. Additionally, unresolved multiplicity was a concern. If two or more massive stars were orbiting close together and appeared as a single point of light, the combined luminosity could be misinterpreted as belonging to one extremely massive star. Without sufficient angular resolution, distinguishing between a single extreme star and a tight binary system was difficult. As instruments improved, particularly with the deployment of the Hubble Space Telescope, the central region of R136 was examined with far greater clarity. Hubble's sharp imaging resolved many of the brightest sources individually, reducing uncertainty about whether the extreme luminosity was due to blending. With better resolution came more precise spectroscopy. Detailed spectral analysis allowed astronomers to determine effective temperatures, surface gravities, wind velocities, and chemical abundances. These parameters fed into sophisticated stellar atmosphere models, producing revised luminosity and mass estimates. And that is when the numbers began to shift upward. One particular object, later designated R136A1, stood out as exceptionally luminous even within an already extreme cluster. Its spectral classification suggested a very hot, hydrogen-rich, Wolf-Rayet-like star, indicative of enormous mass and powerful stellar winds. When models were applied carefully, the inferred mass was not just above 100 solar masses. It pushed significantly beyond the classical ceiling. At first, skepticism was natural. Were the distance measurements correct? The Large Magellanic Cloud's distance is well constrained, but small uncertainties can affect luminosity calculations. Were extinction corrections accurate? Dust can dim light and distort color measurements. Were stellar atmosphere models sufficiently reliable in this extreme regime? Each of these questions was examined. As data accumulated and modeling improved, the conclusion became harder to dismiss. The luminosity was real, the temperature was real, the wind properties were real. And when those factors were combined, the implied mass did not comfortably sit below 150 solar masses. It exceeded it. The discovery was not a single dramatic announcement. It was a gradual tightening of constraints as better data replaced older assumptions. With each refinement, the estimated mass remained stubbornly high. The rule had not yet collapsed, but it was clearly under pressure. R136 was no longer just an unusually bright cluster. It was becoming the site of a potential boundary violation, and at its center, one star was forcing astronomers to reconsider how absolute the upper mass limit truly was. The breakthrough did not come from a single dramatic image. It came from resolution. For years, the central region of R136 was known to be extraordinarily luminous, but its structure remained partially unresolved. Even when astronomers understood that R136 was a cluster rather than a single supermassive object, the brightest core members were still difficult to separate cleanly with ground-based observations. Light from multiple massive stars blurred together. Spectral lines overlapped. Luminosity estimates carried uncomfortable uncertainty. Everything changed when high-resolution imaging from the Hubble Space Telescope began dissecting the cluster with precision impossible from Earth's surface. Freed from atmospheric distortion, Hubble resolved the dense core of R136 into individual luminous stars. What once appeared as a saturated central glow became a collection of discrete, intensely bright objects packed within a few light years. One of them stood out. R13601 was not merely one of many bright stars, it was the brightest of the brightest. Its luminosity was extreme, even relative to neighboring massive stars in the same cluster. That alone was striking. In a cluster already populated by giants, one object still dominated. But brightness alone does not give mass. To estimate mass, astronomers needed spectra. High-resolution spectroscopy allowed measurement of the star's effective temperature and wind properties. R136A1 exhibited characteristics of an extremely hot, hydrogen-rich, Wolf-Rayet-like star. These types of stars are rare and represent some of the most massive and luminous stellar objects known. The spectral lines indicated intense stellar winds with high terminal velocities. Emission features revealed strong mass loss. The effective temperature was estimated to be above 50,000 Kelvin, far hotter than typical O-type stars. Temperature and luminosity together define a star's position on the Hertzsprung-Russell diagram. By comparing R136A1's location on that diagram with theoretical stellar evolution tracks, astronomers could infer its mass, and the inferred mass was staggering. Initial refined estimates suggested a current mass well above 100 solar masses, possibly near or exceeding 200. Even more dramatic were estimates of its initial mass at birth, accounting for mass lost through stellar winds during its short lifetime. Models suggested that R136A1 may have formed with an initial mass approaching or even exceeding 300 solar masses. That number was not a small deviation from the classical ceiling, it was double. Naturally, the reaction was caution. Stellar atmosphere models at such extreme luminosities push into regimes where assumptions become fragile. Opacity tables, wine clumping factors, and evolutionary tracks all influence derived mass. If any one of these inputs were wrong, the mass estimate could shift. But repeated analyses using updated models continued to yield extreme values. Different modeling groups, using improved codes and refined assumptions, still found that R136A1's mass could not be comfortably reconciled with the traditional 150 solar mass ceiling. The discovery was not a headline-grabbing explosion. It was something more unsettling: consistency. As data improved, the star remained too massive. This forced a reframing of the question. Instead of asking whether the Eddington limit was wrong, astronomers began asking under what conditions a star might temporarily exceed the previously assumed formation boundary. Perhaps the upper limit was not a hard wall but a soft one, environment-dependent, sensitive to metallicity, density, and cluster dynamics. The Hubble observations did not overthrow theory. They complicated it. R136A1 was not a violation of physics. It was a demonstration that extreme environments can push physics into corners where approximations break down. And from that point forward, the upper mass limit was no longer refused to shrink back under 100, refused to shrink back under 150 solar masses. Spectroscopy is where brightness becomes physics. An image can show that a star is luminous. A spectrum reveals what that luminosity means. When astronomers began analyzing the detailed spectrum of R136A1, they were not just measuring how bright it looked. They were decoding its temperature, wind velocity, chemical composition, and surface gravity. The spectral lines were extreme. R13601 displayed strong emission features characteristic of very hot, massive stars in an early evolutionary phase. Its classification placed it among hydrogen-rich Wolf-Rayet-like stars, specifically of the WN subtype. These are not the stripped, helium-dominated Wolf-Rayet stars seen later in stellar evolution. These are objects so massive and luminous that they resemble Wolf-Rayet stars while still burning hydrogen in their cores. That alone implied extraordinary internal conditions. The effective temperature derived from spectral modeling exceeded 50,000 Kelvin. At such temperatures, the star's radiation is heavily weighted toward ultraviolet wavelengths. Its photon output is not just visually bright, it is energetically intense, capable of ionizing large volumes of surrounding gas. Temperature feeds directly into luminosity calculations. Using the Stefan Boltzmann law, luminosity depends on both temperature and radius. Once temperature is constrained from spectral lines and radius is inferred from brightness and distance, luminosity follows. And R13601's luminosity was enormous, millions of times greater than that of the Sun. But the spectrum revealed more than temperature. The width and structure of emission lines showed powerful stellar winds. These winds were not subtle. Terminal velocities reached thousands of kilometers per second. The mass loss rate inferred from line profiles suggested that the star was shedding material at an extraordinary pace. The atmosphere was not static. It was expanding outward under intense radiation pressure. Modeling these winds required sophisticated non-local thermodynamic equilibrium, non-LTE codes. At such extreme luminosities, simple approximations fail. Radiation fields interact strongly with the outer layers. Line-driven wind theory had to be carefully applied to interpret the observations correctly. Even with these complexities, the spectral analysis kept pointing toward the same conclusion. The luminosity was real, the temperature was extreme, and the wind properties were consistent with a star of extraordinary mass. Surface gravity estimates from spectral features also supported high mass. Lower mass stars with similar luminosities would exhibit different line broadening and different pressure-sensitive features. The data did not match a lower mass imposter scenario. Of course, uncertainties remained. Wind clumping can affect inferred mass loss rates. Distance uncertainties influence luminosity calculations. Metallicity assumptions affect opacity modeling, but when independent analyses refine these parameters, the star's position in the Hertzsprung-Russell diagram remained far above the traditional ceiling. The spectral data did not scream error, it screamed extreme. What made this especially significant was that R13601 was not alone. Other stars in the R136 cluster also exhibited very high masses, some above 100 solar masses. The cluster as a whole appeared to host a population of stars that pressed hard against the expected upper boundary. But R13601 was the most extreme case. The spectral analysis did not simply identify a very hot star. It identified a star whose luminosity required a mass well beyond what classical formation models were comfortable allowing. In astrophysics, spectra are evidence. They carry fingerprints of temperature, composition, velocity, and pressure. And in the case of R13601, those fingerprints consistently pointed toward a mass that refused to sit below the traditional limit. The numbers were not guessed, they were extracted from light itself. And light, ironically, was now revealing that its own limiting power might not be as absolute as once believed. Calculating the mass of an object like R13601 is not as simple as putting it on a scale. There is no direct measurement. Mass must be inferred from the combination of luminosity, temperature, and theoretical stellar evolution models. The process begins with luminosity. Because R13601 resides in the Large Magellanic Cloud, its distance is relatively well constrained, roughly 160,000 light-years. That distance matters. If you know how bright a star appears and you know how far away it is, you can calculate its intrinsic luminosity. Once high-resolution imaging from the Hubble Space Telescope resolved R13601 clearly, astronomers could measure its brightness without confusion from unresolved neighbors. Combined with distance and extinction corrections for interstellar dust, this yielded an intrinsic luminosity that was staggering, on the order of several million times that of the Sun. Luminosity alone does not directly give mass, but in massive stars, luminosity and mass are tightly linked through stellar structure theory. Next comes temperature. Spectral modeling indicated an effective surface temperature exceeding 50,000 Kelvin. With both luminosity and temperature known, the Stefan-Boltzmann relation can be used to determine the star's radius. From luminosity L equals 4 πr squared sigma t to the fourth power, L equals 4 pi r squared sigma t to the fourth power. Radius follows once L and T are constrained. For R136A1 Dasu, the radius was large, but not absurdly so. This is important. The star was not the largest by physical size. Its extremeness came from its mass and luminosity, not an unusually bloated radius. Now the critical step, placing the star on theoretical stellar evolution tracks. These tracks are computed using detailed models of stellar interiors that simulate how stars of different initial masses evolve over time. For extremely massive stars, these tracks include effects such as strong radiation pressure, intense mass loss, and changes in internal composition due to fusion. When R136A1's observed luminosity and temperature were plotted against these tracks, the only models that matched its position corresponded to very high masses, Current mass estimates settled in the range of roughly 170 to 230 solar masses. Even more striking were the inferred initial masses at birth, which some models placed near or above 250 to 300 solar masses before accounting for early mass loss. That number is what shook the field, because even the lower bound of the estimated range exceeded the classical 150 solar mass ceiling. Naturally, astronomers examined every possible source of error. Could R136A1 actually be an unresolved binary? If two massive stars were orbiting closely and appearing as one, the combined luminosity could be misleading. However, spectroscopic monitoring did not reveal clear signatures of binarity at the level required to explain away the extreme luminosity. Could wind clumping affect the luminosity estimate? Clumping influences mass loss calculations more than total luminosity, and even conservative assumptions did not bring the mass comfortably below the traditional limit. Could the stellar evolution models themselves be inaccurate at such high masses? Possibly, but multiple independent modeling efforts using updated physics continued to produce extreme mass estimates. The conclusion was not made lightly. It emerged from iterative refinement. With each improvement in atmosphere modeling, each update in opacity tables, each recalibration of wind parameters, R136A1 remained massive, uncomfortably massive. The calculation was not a wild extrapolation. It was a consistent result from data anchored in measurable quantities: brightness, distance, temperature, and spectral properties. For decades, the upper mass limit had been supported by both theory and observation. Now, theory and observation were aligning again, but in a way that suggested the ceiling was higher than expected. The mass of R136A1 was not declared recklessly. It was derived cautiously, and even under cautious interpretation, it stood far above 150 solar masses. The boundary had not shattered explosively, it had quietly shifted upward. When the first refined mass estimates for R136A1 began circulating, the reaction was not celebration, it was suspicion. Astrophysics has learned caution the hard way. When a measurement appears to violate a long-standing theoretical boundary, the first assumption is not that the theory has failed. It is that something in the interpretation may be wrong. R13601 was estimated to be far above the classical upper mass limit. That alone was enough to trigger skepticism. But skepticism in science is not denial. It is a checklist. The first concern was multiplicity. Could R13601 actually be two or more massive stars orbiting so closely that they appear as a single point of light? In dense clusters like R136, close binaries are common. If two very massive stars were unresolved, their combined luminosity could mimic one extreme object. High-resolution imaging from the Hubble Space Telescope helped reduce that uncertainty. But imaging alone cannot rule out tight spectroscopic binaries, so astronomers looked at spectral line profiles over time. If two stars were orbiting each other, Doppler shifts in their spectral lines would reveal periodic motion. No such clear periodic signatures appeared at the level required to explain away the extreme luminosity. While small companions could not be completely excluded, the data did not support a massive hidden binary capable of having the inferred mass. The second concern was model dependence. Mass estimates at such extremes rely heavily on stellar atmosphere models. These models must account for non-local thermodynamic equilibrium conditions, strong radiation fields, and powerful winds. If the models were systematically overestimating luminosity or misinterpreting line strengths, the derived mass could be inflated. So independent groups reanalyzed the data using updated modeling codes. Opacity tables were refined, wind clumping factors were reconsidered. The star was placed against different evolutionary tracks, computed with varying assumptions about metallicity and rotation. The numbers shifted slightly, but they did not collapse below the traditional ceiling. Another concern involved distance. If the distance to the Large Magellanic Cloud were significantly overestimated, luminosity would be overestimated as well. However, the distance to the Large Magellanic Cloud is one of the best constrained extragalactic distances in astronomy. Uncertainty exists, but not nearly enough to explain the discrepancy. Dust extinction was also carefully examined. Intervening dust can dim and redden starlight, complicating luminosity calculations. Yet extinction corrections were applied using multi-wavelength observations, and again, reasonable adjustments did not bring the mass into comfortable alignment with the old limit. There was also the possibility that stellar evolution models at extreme masses were incomplete. Perhaps stars above 150 solar masses evolved differently than predicted. Perhaps enhanced mass loss in early phases had not been fully accounted for. But even when conservative assumptions were applied, assuming stronger winds or slightly lower luminosities, R13601 remained well above 100 solar masses and frequently above 150. What made the doubt more interesting is that it did not come from denial of data. It came from the weight of precedent. For decades, the upper mass limit had been supported by both theory and observation. Breaking it required more than a single measurement. Yet R13601 was not alone in the cluster. Several other stars in R136 also appeared to push near or beyond the classical boundary. The pattern suggested that the environment itself might be capable of producing unusually massive stars. Gradually, the tone shifted. Instead of asking whether the star was real, the conversation moved toward understanding how it could exist within the framework of stellar physics. Perhaps the upper mass limit was not universal but environment-dependent. Perhaps metallicity, cluster density, and formation dynamics allowed brief excursions above the old ceiling. The doubt did not vanish. It transformed. R13601 was not dismissed. It was scrutinized. And after years of analysis, the most conservative conclusion was not that the star fit comfortably within the old boundary, but that the boundary itself needed adjustment. The skepticism had done its job. The mass remained extreme, and the rule, while not broken beyond repair, was no longer as rigid as it once appeared. Skepticism did not fade quickly. It intensified. When a star appears to weigh more than 200 times the mass of the Sun, the reaction inside the astrophysics community is not excitement. It is pressure testing. Every assumption becomes suspect. Every input parameter is re-examined. The burden of proof shifts entirely onto the measurement. R13601 did not merely nudge the upper mass limit, it potentially doubled it. That scale of deviation forces fundamental questions. If the classical ceiling was around 150 solar masses, and this object's inferred initial mass approached 250 or even 300 solar masses. Then either the environment of the Tarantula Nebula had unlocked a new formation pathway, or one of the foundational assumptions about radiation pressure and stellar feedback was incomplete. The first wave of doubt centered on multiplicity, but deeper skepticism went further. In extremely dense clusters like R136, crowding is severe. Even with high-resolution imaging, line-of-sight alignment can produce composite spectra. Could the light being analyzed belong to a tight multiple system whose components were nearly identical in temperature and luminosity? That would make spectral disentanglement exceptionally difficult. However, detailed line profile analysis did not reveal the kind of complex blended signatures expected from equal mass binaries at the scale required to reduce the inferred mass dramatically. The line widths and emission features behaved as if dominated by a single extremely luminous source. Small companions were possible, but not massive enough to explain away half the luminosity. Then came the issue of stellar atmosphere modeling at extreme luminosities. At such high masses, stars are no longer comfortably described by classical approximations. Radiation pressure becomes a major fraction of total pressure. The outer envelope approaches Eddington instability. Winds are optically thick. Clumping is significant. Theoretical models must account for non-local thermodynamic equilibrium, multi-line scattering, and detailed radiative transfer in accelerating outflows. If those models were flawed, even subtly, the derived luminosity, and therefore mass, could shift. Multiple independent modeling efforts attacked this problem. Codes were refined, opacity tables updated, clumping factors reevaluated, rotation rates incorporated. Each iteration adjusted parameters within physically reasonable bounds. The result was not a collapse of the mass estimate, it was persistence. Even conservative modeling produced present-day mass estimates well above 100 solar masses, and frequently above the traditional 150 threshold. Initial mass estimates remained extreme, often pushing toward or beyond 250 solar masses before accounting for early wind-driven mass loss. Distance errors were examined next. Luminosity scales with the square of distance. If the distance to the Large Magellanic Cloud were overestimated by even 10%, luminosity would shift noticeably. But the distance to the Large Magellanic Cloud is among the best calibrated extragalactic measurements in astronomy, anchored by multiple independent methods, C-feed variables, eclipsing binaries, and geometric calibrations. The uncertainty margin was nowhere near sufficient to erase the discrepancy. Dust extinction corrections were also stress-tested. Multi-wavelength observations reduced uncertainty. Even when extinction values were pushed to conservative extremes, the star remained extraordinarily luminous. The skepticism gradually transformed from, "Is the measurement wrong?" to, "What does this mean for the limit?" The classical upper mass boundary had been supported by physics that was not invalidated. Radiation pressure still scales steeply. The Eddington limit still exists. Stellar winds still remove mass aggressively. None of those mechanisms vanished. What changed was the realization that the limit might not be a hard wall. It might be a threshold that can be exceeded temporarily in sufficiently extreme environments. This distinction matters. A hard limit implies impossibility. A soft limit implies instability, but not prohibition. R13601 appeared to be living at the edge of that instability. Its luminosity suggested it was operating very close to the Eddington limit. Its winds were violent. Its lifetime would be short, but it existed, and existence is decisive. The doubt did not disappear. It evolved into refinement. Instead of rejecting the star, the field began adjusting its expectations. The upper mass limit was no longer treated as a universal constant. It became environment-dependent, sensitive to metallicity, density, and formation dynamics. R136A1 did not break stellar physics. It forced stellar physics to acknowledge its flexibility at the extremes. And that is more unsettling than a simple contradiction. One of the biggest misconceptions about R13601 is that it must be the physically largest star ever observed. It is not. Mass and size are not the same thing. When people imagine a star hundreds of times the mass of the Sun, they often picture something swollen to impossible dimensions, dwarfing red supergiants like Betelgeuse. But R136A1 is not a bloated red giant. It is not a cool, expanded envelope drifting at low density. It is a compact, violently hot main sequence monster. Its extremeness comes from mass and luminosity, not sheer radius. The confusion begins with intuition. In everyday experience, more mass usually means more size. Add more material, and the object becomes larger. But stars do not follow simple scaling rules. Their structure is governed by hydrostatic equilibrium and energy transport mechanisms, not simple accumulation. For massive stars, increasing mass increases core temperature dramatically. Higher core temperature increases radiation pressure. Radiation pressure supports the outer layers more efficiently, preventing runaway gravitational collapse, but it also reshapes internal structure. The result is not an endlessly expanding sphere. Instead, extremely massive stars tend to remain relatively compact compared to red supergiants. R136A1's radius is estimated to be on the order of a few dozen solar radii. Large, yes, but nowhere near the hundreds or thousands of solar radii seen in evolved red giants. This matters because luminosity depends on both radius and temperature. Using the Stefan Boltzmann law, luminosity is proportional to radius squared times temperature to the fourth power R13601 achieves its enormous luminosity, not by being enormously inflated, but by being extraordinarily hot. Surface temperatures above 50,000 Kelvin mean the star radiates immense energy per unit area. Even a moderately large radius combined with that temperature yields luminosities millions of times that of the Sun. The distinction between mass and radius also highlights the difference between stellar evolutionary stages. Red supergiants like Betelgeuse are physically enormous but relatively cool. Their luminosity comes from size more than temperature. They are evolved stars nearing the end of their lives. R13601, in contrast, is extremely young. It is still burning hydrogen in its core. It is compact relative to its mass, incredibly dense in its interior, and radiating energy at a ferocious rate because of core fusion intensity, not envelope inflation. This compactness actually reinforces the mass estimate. If R13601 were extremely luminous and also enormously bloated, there might be alternative interpretations involving instability or transient expansion phases, but its observed radius, combined with its temperature and wind properties, fits best with a very high-mass main sequence star. There is another layer to this distinction. As stellar mass increases, radiation pressure becomes a dominant contributor to internal support. In the most massive stars, radiation pressure accounts for a significant fraction of total pressure, especially in the outer layers. This leads to a star that is less centrally condensed than lower mass stars. Yet even with strong radiation pressure, gravity still holds the structure together. The star does not inflate arbitrarily. The internal pressure gradient adjusts to maintain equilibrium, so R136A1 is not a balloon, it is a furnace. Its core density and temperature are extreme. Its outer layers are driven by powerful radiation pressure. Its winds are intense. But its radius does not scale proportionally with its mass. This distinction is important for understanding how it can exist at all. If mass scaled directly into enormous size, the star might become dynamically unstable much earlier. Instead, its structure allows it to sustain extraordinary mass while remaining relatively compact and hot. Mass determines gravitational strength and fusion rate. Temperature determines energy output per unit surface area. Radius determines how that energy is distributed spatially. R136. A1's extremeness is primarily an internal story, a story of core pressure, fusion intensity, and radiation dominance, not an external story of sheer physical expansion. That is why calling it the biggest star is misleading. It is not the largest by size. It is the most massive by gravitational content. And in stellar physics, mass is the deeper variable. Mass controls core temperature. Core temperature controls fusion. Fusion controls luminosity. Luminosity controls radiation pressure. And radiation pressure defines how close the star lives to the brink of self-destruction. Understanding the distinction clears one of the most common misunderstandings. R136A1 is not impressive because it fills more space. It is impressive because it contains more gravity than any star we have directly measured, and yet it has not collapsed under its own weight. That is the true anomaly. Luminosity is where R136A1 stops being impressive and starts being disturbing. Its brightness is not marginally higher than other massive stars. It is not a bit more luminous. It radiates on the order of 8 to 10 million times the luminosity of the sun. That number is difficult to visualize, so break it down. The sun produces about 3.8 times 10 to the power of 26 watts of energy every second. Multiply that by roughly 10 million. That is the power output of R136A1 continuously without pause, every second. This is not surface glow. This is energy released by nuclear fusion in the core at a rate so extreme that the star will exhaust its fuel in only a few million years. While the sun will live for about 10 billion years, R136A1's lifetime is expected to be closer to 2 million. It burns brighter because it burns faster, and the scaling is merciless. In massive stars, luminosity scales roughly as mass to the third power. That means doubling mass does not double brightness. It increases it by about 8 times. At the extreme high mass end, the relationship becomes even steeper and more complex due to radiation pressure dominance. For R136A1, luminosity is not just a number. It is a structural force. At millions of solar luminosities, radiation pressure becomes a major fraction of total internal pressure. In its outer layers, the star lives close to the Eddington limit. the point where outward radiation force balances inward gravity. This is not theoretical proximity. It is measured proximity. Astronomers estimate that R13601 operates at a significant fraction of its Eddington luminosity. That means gravity and radiation are nearly matched in its envelope. A small increase in luminosity could destabilize outer layers further. A small drop in mass could alter equilibrium. The star is not comfortably stable. It is dynamically balanced at extreme conditions. Its surface temperature exceeding 50,000 Kelvin means most of its energy is emitted in ultraviolet wavelengths. That ultraviolet radiation is capable of ionizing vast regions of surrounding gas. The Tarantula Nebula glows partly because of stars like this flooding it with ionizing photons. The ionizing photon output alone is staggering. R13601 emits enough ultraviolet radiation to carve enormous H2 regions, volumes of ionized hydrogen hundreds of light years across when combined with other massive stars in the cluster. Its radiation shapes its environment on interstellar scales, and yet luminosity does not simply illuminate space. It drives winds. At such extreme brightness, photons scatter repeatedly in the star's atmosphere, transferring momentum outward. This drives stellar winds moving at thousands of kilometers per second. The wind momentum is directly tied to luminosity. Higher luminosity means stronger wind acceleration. In R13601, the wind mass loss rate is enormous. It sheds material continuously. That mass loss slightly reduces its gravitational binding, which in turn influences how close it sits to the Eddington limit. The relationship between luminosity, wind strength, and mass is tightly coupled. There is another subtlety here. At these luminosities, radiation pressure is not just pushing on electrons through simple Thomson scattering. Line opacity becomes critical. Photons are absorbed and re-emitted by specific atomic transitions, enhancing momentum transfer. This line-driven wind mechanism becomes more efficient as luminosity rises, making the star even more prone to losing mass. The paradox becomes clear. The more luminous the star, the more it destabilizes itself. Yet despite emitting millions of times the sun's energy, R136A1 has not blown itself apart. That fact alone tells you something important. The Eddington limit is not a sharp explosion trigger. It is a threshold for instability, not instant destruction. A star can approach it closely and survive, but at the cost of violent winds and short lifespan. Luminosity also defines how visible the star is across cosmic distances. If R136A1 were placed at the distance of the Orion Nebula, it would dominate the night sky. If it replaced the Sun in our solar system, Earth would not survive even briefly. The radiation intensity would sterilize the planet instantly. The heliosphere would be overwhelmed. The solar system would become an ionized shell. But astrophysics does not care about human survival. What matters physically is that such luminosity implies extreme core conditions. Core pressures and temperatures must be high enough to sustain that output. The fusion rate must be enormous. The hydrogen fuel consumption rate must be extraordinary. This is why luminosity is a proxy for mass. You cannot sustain 8 to 10 million solar luminosities without a core massive enough to generate that energy. And that core mass ties directly back to the total gravitational mass of the star. In simpler terms, you cannot fake that brightness. If the luminosity measurement is correct, and repeated analyses confirm that it is, then the mass must be extreme. There is no low mass configuration capable of sustaining that output for more than a transient flash. 13601 is not just bright, it is operating at a level of energy output that forces stellar physics into its most extreme regime, where radiation pressure rivals gravity, where winds reshape structure continuously, and where lifetime collapses from billions of years to mere millions. That is what makes its luminosity dangerous to old assumptions. Because luminosity is not cosmetic, luminosity is evidence. At the heart of R136A1 lies the real reason it is so extreme: the core. Surface temperature tells you how hot the star looks. Luminosity tells you how much energy it emits. But the core temperature tells you how violently fusion is proceeding. And in a star this massive, fusion is not gentle. In a star like the Sun, core temperature is about 15 million Kelvin. Hydrogen fuses primarily through the proton-proton chain, a relatively slow and stable process. That slowness is why the Sun lives for billions of years. R13601 operates in a completely different regime. Its core temperature is estimated to exceed 40 million Kelvin, possibly pushing toward 50 million. At these temperatures, hydrogen fusion is dominated by the CNO cycle, a catalytic process involving carbon, nitrogen, and oxygen nuclei. The CNO cycle is extremely temperature sensitive. In the proton-proton chain, fusion rate increases modestly with temperature. In the CNO cycle, fusion rate can scale roughly as temperature to the 15th or even 20th power in certain regimes. That means a small increase in temperature produces a massive increase in energy output. This sensitivity is part of why very massive stars are inherently unstable. If the core contracts slightly, temperature rises. If temperature rises, fusion accelerates dramatically. If fusion accelerates, energy output spikes. That increased energy raises radiation pressure, pushing the star outward and cooling the core again. The system constantly self-corrects, but at extreme masses, the corrections are violent. R136. A1's core is not just hot, it is under extraordinary pressure. Gravity compresses hundreds of solar masses into a relatively compact volume. Radiation pressure contributes significantly to total pressure, but gas pressure from particle collisions still plays a major role in the core. The balance between radiation and gas pressure determines internal stability. In stars like R136A1, radiation pressure can account for a large fraction of total pressure, far more than in lower mass stars. That changes how energy is transported and how the star responds to perturbations. Another consequence of extreme mass is convective core size. In very massive stars, the convective core occupies a large fraction of the total stellar volume. Convective motion efficiently transports energy outward from the fusion region, mixing fresh hydrogen into the core. This mixing prolongs hydrogen burning compared to what would occur in a purely radiative core. But it does not extend lifetime dramatically. Even with efficient mixing, the fusion rate is so high that hydrogen fuel is consumed at an enormous pace. R13601 may burn through a substantial fraction of its hydrogen in just a few million years. To put this in perspective, the Sun converts about 600 million tons of hydrogen into helium every second. R13601 converts vastly more, orders of magnitude more, because its luminosity is millions of times greater. This fuel consumption rate defines its fate. The core does not merely fuse hydrogen. It will rapidly progress through helium burning and possibly beyond, depending on mass loss evolution. At these masses, the internal structure approaches regimes where exotic instabilities can occur, including pair production effects at later stages. Even during hydrogen burning, the internal radiation field is so intense that the star sits near the Eddington limit globally, not just at the surface. The fusion engine inside R136A1 is not a scaled-up version of the Sun's. It is a qualitatively different machine. It operates in a radiation-dominated environment with fusion rates hypersensitive to temperature and with structural responses that are more dramatic. And this is where mass matters most. You cannot achieve such core conditions without enormous gravitational compression. The fusion rate required to produce millions of solar luminosities demands a core mass consistent with the extreme mass estimates derived from luminosity and spectroscopy. The core is the proof. If R136A1's luminosity is real, and it is, then the core must sustain fusion at a rate only possible in a star far above traditional upper limits. And that means the internal physics does not merely tolerate its mass, it demands it. The violence in the core explains the violence at the surface, the extraordinary brightness, the relentless stellar winds, the short lifetime. Everything begins in the furnace at the center, where gravity squeezes matter so intensely that light is produced in quantities once thought incompatible with stable stellar structure. Yet it persists. For now, the surface of R136A1 is not calm. It is not a stable photosphere gently radiating light into space. It is an active, unstable boundary layer where radiation pressure, ionized gas, and extreme luminosity combine to drive continuous mass ejection. At luminosities approaching 10 million times that of the Sun, photons are not merely escaping, they are pushing. Every photon carries momentum. When those photons interact with ions in the stellar atmosphere, they accelerate material outward. This is the foundation of radiation-driven stellar winds. In R13601, those winds are extraordinary. Terminal wind velocities reach thousands of kilometers per second. That means material stripped from the surface does not drift away slowly. It is launched violently into space at speeds fast enough to escape the star's deep gravitational well. The mass loss rate is equally extreme. Estimates suggest that R136A1 loses on the order of 10 to the power of -5 to 10 to the power of -4 solar masses per year. That may seem abstract, but over a few million years, that translates to tens of solar masses expelled into the surrounding nebula. The star is actively dismantling itself. This is not a temporary flare or occasional eruption. It is a continuous process driven by the coupling between luminosity and opacity. At such high luminosities, line-driven winds become incredibly efficient. Photons are absorbed by atomic transitions in the outer layers and re-emitted, transferring momentum each time. The cumulative effect is a sustained outward acceleration of gas. The outer envelope of R13601 lives close to the Eddington limit. In some regions, local conditions may even exceed it. That creates pockets of instability where gravity barely holds material down. Small perturbations can trigger enhanced mass loss. Wind clumping adds another layer of complexity. Observations show that stellar winds are not perfectly smooth. They form dense clumps interspersed with lower density regions. Clumping can increase the effective mass loss rate and complicate interpretation of spectral lines. It also makes the star's outer layers more chaotic and less predictable. This instability is not incidental. At these masses, the star cannot exist without losing material. The radiation field is simply too intense. The stellar wind is the mechanism by which the star tries to re-establish equilibrium. Excess luminosity drives mass loss. Reduced mass slightly lowers gravitational binding. The star continually adjusts. But there is a limit to how long this balance can hold. If mass loss is strong enough, the star's evolution can shift dramatically. The outer hydrogen envelope may be stripped away earlier than expected. The star may transition into a hydrogen-poor Wolf-Rayet phase sooner. Its final fate depends heavily on how much mass it retains before core collapse. There is also the effect on the surrounding environment. The wind from R136A1 injects enormous kinetic energy into the Tarantula Nebula. It sculpts cavities, compresses nearby gas, and influences future star formation. The star is not merely a luminous object. It is a dynamical engine altering its cluster. The irony is clear. Radiation pressure is what makes the star so bright. Radiation pressure is also what erodes it. The stronger the luminosity, the stronger the wind. The stronger the wind, the faster the star loses mass. This feedback reinforces the idea that extremely massive stars should not remain extremely massive for long. Even if formation allows a star to exceed traditional limits, evolution quickly begins pulling it back down. And yet, R136A1 still exists at this mass, which suggests that either its formation was exceptionally rapid, allowing it to reach extreme mass before winds intensified fully, or that mass loss prescriptions in older models were too aggressive at high masses, especially in lower metallicity environments like the Large Magellanic Cloud. Metallicity matters because wind strength depends on line opacity, which depends on heavy elements. Lower metallicity reduces line-driven wind efficiency slightly, potentially allowing the star to retain more mass than a similar star in the Milky Way. That small shift can be decisive at the extreme upper end. Still, even with reduced metallicity, the wind is brutal. R136A1 is not a stable monument. It is a transient peak. Its present mass is likely already lower than its birth mass. Every year it is lighter than the year before, and that erosion is not optional. It is written into the physics of light interacting with matter at extreme luminosities. The star survives not because winds are absent, but because they are not yet strong enough to dismantle it completely. It lives on borrowed mass, and its future depends on how quickly that mass continues to disappear. At extreme mass, stability stops being a comfortable concept. R136A1 does not sit peacefully on the main sequence the way the Sun does. It exists in a regime where small changes in internal conditions can produce disproportionately large structural responses. It lives close to theoretical thresholds that most stars never approach. The first instability comes from radiation dominance. In lower mass stars, gas pressure dominates the interior. Particle collisions support the star against gravity. In extremely massive stars like R136A1, radiation pressure becomes a major fraction of total pressure, especially in the outer layers. When radiation pressure approaches parity with gravity, the star becomes more sensitive to perturbations. If luminosity increases slightly, radiation pressure can temporarily exceed gravitational binding in some regions. That can trigger enhanced mass loss, envelope inflation, or local density inversions. The second instability is tied to temperature sensitivity of fusion. As discussed earlier, hydrogen burning in such massive stars proceeds through the CNO cycle. That process is extremely temperature dependent. A small rise in core temperature can produce a large increase in energy output. If core contraction occurs even slightly, fusion accelerates rapidly. If fusion accelerates, radiation pressure spikes. If radiation pressure spikes, the outer layers respond dynamically. This creates a feedback loop that must constantly self-correct. The star exists in a state of dynamic equilibrium, not static calm. Then there is envelope inflation. Near the Eddington limit, the outer layers of a star can expand significantly because radiation pressure weakens effective gravity. This does not necessarily mean the star becomes a red supergiant, but it can create extended low-density regions in the outer envelope. These inflated envelopes are more susceptible to instabilities and enhanced mass loss. Opacity-driven instabilities may also occur. In certain temperature regimes, opacity increases sharply due to ionization zones. These opacity bumps can trap radiation temporarily, increasing local pressure and potentially driving pulsations. In massive stars close to the Eddington limit, such effects can amplify structural oscillations. There is also the looming specter of pair production, though that lies later in evolution. In the most massive stars, when core temperatures become sufficiently high during advanced burning stages, energetic photons can convert into electron-positron pairs. This reduces radiation pressure because energy that once supported the star is suddenly diverted into particle rest mass. If this happens in a sufficiently massive core, it can trigger catastrophic collapse and explosive oxygen burning. R136A1 is likely not yet in that stage, but its extreme mass means it is closer to that regime than most stars will ever be. Rotation adds another destabilizing factor. Massive stars often rotate rapidly. Rotation reduces effective gravity at the equator and can enhance mass loss. If R136A1 rotates significantly, centrifugal forces would further complicate its equilibrium, making the outer layers even more prone to instability. Magnetic fields, if present at significant strength, could also channel winds and alter mass loss geometry, though their role in such extreme stars remains an active area of research. All of these factors converge toward the same picture. R136A1 is not stable in the everyday sense. It is conditionally stable. Its existence depends on delicate balance between gravity, radiation pressure, fusion rate, wind mass loss, and possibly rotation. It is perched near theoretical boundaries that were once thought to be unreachable. This is what makes its mass so important. If the star were only 100 solar masses, most of these instabilities would be less extreme. At 200 solar masses or more, they intensify dramatically. The closer a star gets to the Eddington limit, the more sensitive it becomes to small changes in luminosity or opacity. The classical upper mass limit assumed that such instabilities would prevent long-term survival above roughly 150 solar masses. R13601 shows that survival is possible, at least temporarily, but it does not show that survival is comfortable. The star is likely burning through hydrogen at an extraordinary rate. Its wind is continuously eroding its mass. Its envelope may be marginally stable. Its core is pushing fusion physics into the uppermost regime we can model with confidence. It is not breaking physics, it is testing it. And the fact that it exists at all suggests that the boundary between possible and impossible in stellar mass is more flexible than once believed, but not infinitely so. R13601 is not a new normal, it is a peak, and peaks are rarely stable for long. R13601 will not die quietly. A star this massive does not fade into a white dwarf or gently shed its outer layers. Its death will be violent, and the exact form that violence takes depends almost entirely on how much mass it manages to retain before core collapse. Right now, R136A1 is still burning hydrogen in its core, but it is doing so at a rate that guarantees a short life, probably on the order of 2 million years total. Once hydrogen is exhausted in the core, it will begin fusing heavier elements in successive stages: helium, then carbon, neon, oxygen, and possibly silicon. Each stage burns faster than the one before it. Helium burning lasts far less time than hydrogen burning. Carbon burning lasts less than helium burning. By the time silicon fusion begins, the clock is ticking in days. The ultimate question is this: what will the final core mass be when iron forms? Because iron fusion does not release energy. Once an iron core builds up, pressure support fails. Gravity wins. The core collapses in milliseconds. In lower mass massive stars, say 20 to 40 solar masses, this collapse results in a core collapse supernova, leaving behind either a neutron star or a black hole. But R136A1 does not live in that regime. If it retains enough mass, it could enter a much rarer and more dramatic pathway: pair instability. In extremely massive stars, when the core temperature becomes high enough, energetic gamma-ray photons can convert into electron-positron pairs. This process reduces radiation pressure in the core because photon energy is converted into particle rest mass. Pressure drops. The core contracts rapidly. That contraction raises temperature further, igniting runaway oxygen fusion. If the core mass is within a certain range, roughly 60 to 130 solar masses, this runaway process can completely unbind the star in a pair instability supernova. No remnant remains. The star is obliterated. If the core is even more massive, a slightly different scenario unfolds. Instead of complete disruption, collapse may proceed directly into a black hole after partial instability phases. So what determines which fate R136A1 will meet? Mass loss. If stellar winds strip enough material over its lifetime, the final core mass may drop below the pair instability threshold. In that case, R136A1 could undergo a hypernova-like core collapse, producing an extremely energetic supernova and leaving behind a massive black hole. If mass loss is weaker than expected, perhaps due to lower metallicity in the Large Magellanic Cloud, the core may remain massive enough to enter full pair instability territory. There is also the possibility of a long gamma-ray burst if the star retains rapid rotation and sufficient angular momentum in its core. In that case, collapse could form a black hole surrounded by an accretion disk, launching relativistic jets along the rotational axis. But rotation is uncertain. Strong stellar winds tend to remove angular momentum along with mass, Whether R13601 will rotate rapidly enough at collapse to power such an event remains unknown. What is certain is scale. If R136A1 explodes as a pair instability supernova, the energy release would dwarf typical core collapse supernovae. The explosion could be so luminous that it outshines entire galaxies temporarily. The heavy elements synthesized in the explosion would be enormous in quantity. If it collapses directly into a black hole without full disruption, the resulting remnant could be tens of solar masses or more, potentially contributing to the population of heavy black holes observed in gravitational wave detections. Its death will not be subtle. The Tarantula Nebula will be reshaped by it. Shock waves will propagate through the cluster. Surrounding gas will be compressed or blown away. The chemical composition of the region will change as heavy elements are injected into the interstellar medium. R136A1's life is short. Its death will be explosive. And whichever path it takes, it will push stellar death physics toward its upper extremes, just as its birth pushed stellar formation physics beyond previous comfort zones. It was born near the edge of theory. It will likely die there too. There are two truly catastrophic pathways that dominate discussion when a star like R13601 reaches the end of its life: hypernova collapse and pair instability supernova. Both are violent. Both are rare. But they are not the same. And the difference depends almost entirely on the final core mass. Start with the pair instability mechanism. In extremely massive stellar cores, when temperatures climb above roughly a few billion Kelvin during advanced burning stages, gamma-ray photons in the core become energetic enough to convert into electron-positron pairs. This process is subtle but devastating. Radiation pressure is what supports the core against gravity at these temperatures. But when photons are converted into particle pairs, pressure support drops. Energy that was previously contributing to outward pressure is suddenly tied up in rest mass. Pressure falls. Gravity tightens its grip. The core contracts rapidly. That contraction increases temperature further, and in stars within a specific core mass range, roughly 60 to 130 solar masses, this contraction ignites explosive oxygen fusion. The energy released in that runaway reaction is so immense that it can completely unbind the star. No neutron star, no black hole, nothing left. The entire star is torn apart. This is a pair instability supernova. It is not a typical supernova. It is far more energetic, far more luminous, and capable of synthesizing enormous amounts of heavy elements in a single event. The light curve is broader and more powerful than standard core collapse explosions. Observationally, such events are rare but have been identified in distant galaxies. Now compare that to the hypernova pathway. If the final core mass is slightly lower, or if prior mass loss reduces the star's envelope significantly, the star may avoid full pair instability. Instead, it undergoes conventional core collapse once iron forms in the core. But conventional here is relative. For extremely massive stars, collapse can produce an unusually energetic explosion, a hypernova. In this scenario, the collapsing core forms a black hole, and if sufficient angular momentum remains, an accretion disk forms around it. That disk can power relativistic jets along the rotational axis. If those jets punch through the outer layers of the star and escape into space, they can generate a long gamma-ray burst, one of the most energetic phenomena in the universe. A hypernova does not necessarily destroy the entire star. A massive black hole remnant remains, but the explosion energy can exceed that of ordinary supernovae by an order of magnitude or more. So which fate awaits R13601? It depends on how much mass it retains by the time core collapse occurs. If stellar winds strip the star aggressively over its lifetime, the final core mass may fall below the pair instability threshold. In that case, hypernova collapse becomes more likely. If winds are less efficient, possibly due to the lower metallicity environment of the Large Magellanic Cloud, the core could remain massive enough to trigger full pair instability. Rotation also matters. Strong stellar winds tend to remove angular momentum along with mass. If R13601 loses too much angular momentum, it may not sustain the rotational structure required to produce gamma-ray jets. In that case, even if collapse forms a black hole, it may not generate a gamma-ray burst. The distinction between these outcomes is not academic. A pair instability supernova leaves no remnant and injects vast quantities of heavy elements into its environment. A hypernova leaves behind a massive black hole that may later merge with another black hole, producing gravitational waves. Either outcome would be extreme, and both possibilities exist because the star itself is extreme. The classical upper mass limit was once thought to prevent stars from entering these regimes frequently. If no stars formed above roughly 150 solar masses, pair instability events would be rare and confined mostly to the early universe. R13601 challenges that neat picture. If stars of 200 to 300 solar masses can form under certain conditions, then pair instability and hypernova events may not be restricted to primordial galaxies. They may occur in environments we can observe directly. That is the deeper implication. The death of R136. A1 is not just about one star exploding. It is about whether the upper reaches of stellar evolution are broader than previously assumed, and whether the universe still produces monsters capable of reshaping their surroundings in ways once thought reserved for its earliest epochs. If R13601 does not completely destroy itself in a pair instability supernova, then something enormous will remain, and that something would not be modest. In the case of ordinary massive stars, around 20 to 40 solar masses, core collapse often leaves behind a neutron star or a black hole of perhaps 5 to 15 solar masses. Even more massive progenitors in the Milky Way tend to leave black holes in the range of 10 to 20 solar masses after significant mass loss. R136A1 does not belong to that category. If it avoids total pair instability disruption and instead undergoes core collapse, the resulting black hole could be extremely massive. Depending on how much mass it loses before death, theoretical estimates suggest a remnant possibly tens of solar masses, perhaps even exceeding 50 or more. That scale is important. Black holes in the 30 to 80 solar mass range have already been detected through gravitational wave mergers by observatories like LIGO. For years, astrophysicists struggled to explain how such heavy black holes could form, because classical stellar evolution models in high metallicity environments predicted stronger mass loss, leading to lighter remnants. The existence of R136A1. Like stars in lower metallicity regions, provides a pathway. Lower metallicity reduces wind-driven mass loss. If a star retains more of its mass before collapse, the final black hole can be heavier. The Large Magellanic Cloud, with its reduced metallicity compared to the Milky Way, offers precisely that kind of environment. If R13601 collapses directly into a black hole without fully unbinding itself, the remnant would form in one of the densest clusters nearby. That matters for another reason: mergers. In a dense cluster like R136, massive black holes can interact gravitationally. Over time, close encounters can lead to binary formation and eventual merger. If R136A1 leaves behind a very heavy black hole, it could become part of a binary system that later coalesces, emitting powerful gravitational waves. In other words, the death of R136A1 could contribute directly to the population of black holes detected across the universe today. There is also the question of fallback. During core collapse, not all material may be expelled in a supernova explosion. Some fraction of the outer layers can fall back onto the newly formed black hole, increasing its mass further. In extremely massive stars, fallback can be substantial, potentially boosting the remnant mass beyond what simple core estimates predict. The gravitational binding energy of such a massive star is immense. If the explosion energy is insufficient to unbind the entire envelope, large amounts of material can collapse inward, feeding the newborn black hole. This scenario produces what is sometimes called direct collapse, where the star essentially implodes into a black hole with minimal supernova display. Such an event would be quieter in light, but dramatic in gravity. A black hole of exceptional mass forming in a dense young cluster would alter the cluster's internal dynamics. Its gravitational influence would reshape stellar orbits in its vicinity. Over millions of years, it could sink toward the center through dynamical friction, potentially acting as a seed for more complex interactions. The broader implication is this: if stars above 200 solar masses can form and avoid total pair instability destruction, then the universe has a natural mechanism for producing unusually heavy stellar mass black holes. That shifts the landscape of black hole demographics. It also touches on a deeper question about the early universe. Population 3 stars, the first generation of stars, are believed to have been extremely massive due to low metallicity conditions. If R136A1-like objects exist today in certain environments, they may serve as analogs for understanding those primordial giants. The black hole left behind by R136A1 would not just be a remnant, it would be a data point in the story of how gravity builds extreme objects from the ashes of massive stars. And unlike the star itself, the black hole would not burn out in a few million years. It would persist. Long after the Tarantula Nebula fades and the cluster disperses, that remnant, if formed, would remain as a silent marker of how far stellar mass can be pushed before light finally gives up and gravity takes over completely. For decades, the upper mass limit of stars felt like a solved problem. Radiation pressure rises steeply with luminosity. Luminosity rises steeply with mass. At some point, light pushes back hard enough to prevent further growth. That point was thought to be around 150 solar masses. R136A1 did not shatter that logic. It complicated it. So the final question is not whether limits exist, it is whether the limit is universal. Could 500 solar mass stars exist? The short answer, not comfortably, and probably not for long. The deeper answer is more nuanced. Physics does not forbid a star from briefly assembling at such a mass under extreme conditions. If accretion is rapid enough, if metallicity is low enough, if disk geometry allows radiation to escape anisotropically, and if mergers occur in dense clusters, gravity can temporarily outrun radiation feedback. But sustaining that mass is another matter. At 300 solar masses, radiation pressure already dominates the outer layers. At 400 or 500 solar masses, the star would sit dangerously close to the Eddington limit across much of its structure. Winds would intensify dramatically. Envelope instabilities would likely increase. The star would burn through fuel at an almost absurd rate. Even if such a star formed, it would likely shed mass extremely rapidly. There is also the question of fragmentation. Star-forming clouds tend to break into multiple cores. The more massive the cloud, the more unstable it becomes. Building a single 500 solar mass star without fragmentation requires unusually coherent collapse conditions, something rare even in violent starburst environments. What about the early universe? That is where the ceiling may have been highest. Population 3 stars, the first generation formed after the Big Bang, existed in an environment almost devoid of heavy elements. Low metallicity means low opacity. Low opacity means weaker radiation coupling to gas. That allows higher accretion rates before radiation pressure halts growth. Simulations suggest that primordial stars may have reached several hundred solar masses, perhaps even beyond. But even there, the physics of radiation pressure still applies. The limit shifts upward, but it does not disappear. R136A1 suggests that in modern low metallicity regions like the Large Magellanic Cloud, the ceiling may be closer to 200 to 300 solar masses than 150. That is not a small adjustment. It means the classical upper mass limit was not wrong. It was environment dependent. The universe does not operate with a single global maximum. It operates with thresholds that shift depending on density, metallicity, and cluster dynamics. And that may be the most important lesson. The Eddington limit still governs stars. Radiation pressure still fights gravity. Stellar winds still enforce self-regulation. But the line between possible and impossible is softer than once believed. R136A1 exists at that softened boundary. It is not proof that stars can grow indefinitely. It is proof that nature sometimes pushes harder than our clean theoretical numbers anticipate. Could something larger exist? Perhaps, briefly in extreme environments under rare conditions. But the larger the star, the shorter the life, the stronger the winds, the more violent the death. There is no infinite escalation. Even at 200 or 300 solar masses, instability dominates. Light claws back mass. Fusion accelerates toward collapse. The star burns itself toward catastrophe. So the true upper limit may not be a fixed number carved into physics. It may be a moving ceiling defined by how efficiently gravity can outrun light, and for how long. R136A1 shows that gravity can win longer than we thought, but not